All right, let's talk about how to do calculations with strong acids and bases. So, when you calculate with strong acids and bases, what's nice about it is it's not really different than the calculations you would have done before this point. Because what you've done so far, as a reminder, is you've said, okay, if I'm given the hydrogen ion concentration, I just take the negative log of hydrogen ion concentration, that gives the pH. Simple as that. So here's the thing with strong acids and bases. You got to remember, the definition of what makes an acid strong is that when it is dissolved in water, it dissociates completely. That means every last molecule or formula, depending on who you ask, every last molecule is assumed to split up into ions. That's what dissociation is. So here's what that means in terms of your calculations. If you're given a question where instead of giving you the concentration of the hydrogen ion, it gives the concentration of the acid, you look at the acid, you think, was that on the list of strong acids? Yes, it was. It's a strong acid defined as dissociating 100%. So that means whatever the concentration of the acid is, it's going to give the same concentration of hydrogen ion. Every acid molecule here has one hydrogen ion. So if you have this concentration of acid, you have the exact same concentration of hydrogen ion. So that's what this is saying here. Says if that's the concentration of the acid, 0.10 molar, then, or there's the acid right there, that means when you dissociate it, it's a one-to-one balanced reaction of there's one hydrogen for every molecule of acid, there's one nitrogen for every molecule of acid. So that means the concentration of hydrogen is 0.10 molar, and so is the concentration of nitrate. So if hydrogen is 0.10 molar, then just negative log of 0.10 molar, right here, gives your answer of 1.0. And by the way, do notice, two significant figures, two significant figures. All right, so in terms of the math here, the process, it's nothing new or different. It's using the same thing, just adding the idea that if we give you the concentration of the acid, if it's a strong acid, and only if it's a strong acid can you just take the negative log of concentration and have it be good. If it's a weak acid, totally different calculation. Do not attempt this for a weak acid. All right, now these are other ones you can practice on your own. Here's another example right here. What if instead of me giving you a concentration and asking for the pH, what if I give you the pH and ask for the concentration? Here's the steps laid out. You're going to do the same thing as before. Assume that the concentration of hydrogen is the concentration of the acid. So we're going to take this, calculate a hydrogen concentration, and whatever number that hydrogen concentration is, we're going to give the exact same number as the concentration of the acid. So that's what happens here. We say, all right, if I'm given a pH, you gotta know, either memorize or maybe you might be allowed to use on a test. It depends on what we're doing that particular year. But 10 to the negative pH is hydrogen ion concentration. So 10 to the power of negative 4.7 will give you hydrogen ion concentration. In this case, sit right here, and we're gonna say fine. If that's the hydrogen ion concentration is this, and it's a strong acid, then the exact same number is used as the concentration of the acid overall. So again, easy calculation. So more to practice with, of course. And then one thing that can be confusing is this right here, in the sense of, look, there's two hydrogen ion concentration, or there's two hydrogen ions in this formula. So wait, does that mean you times this concentration by 2 to get concentrated hydrogen ion? There's many cases where the answer is yes, but not this one. This is a special exception. Sulfuric acid is only a strong acid when it loses its first hydrogen ion, but not when it loses its second hydrogen ion. So here's what it means. Even though there's two hydrogens, we're still going to assume that it only loses one out of the two hydrogens, which means concentration of hydrogen ion is still assumed to be, we're simplifying, it's not really the case, but it's assumed to be 0.25 molar. And when I say we're simplifying, some of these other hydrogen ions, the second hydrogen ion, some of them will also release a second hydrogen ion, slightly increase in the hydrogen concentration, but the percent of these that gets released is so small that even if you did take into account, it would not change your answer. You'd still get the same thing from your calculation, especially with only two significant figures. So it's fine. We're just going to say sulfuric acid releases one hydrogen ion only because it's one of the strong acids. And so it's only released one out of its two hydrogen ions, which means hydrogen ion concentration is still 0.25 molar. So you see what I've done here, assumed 0.25 molar hydrogen ion concentration. So we just did as we always do. If you want to calculate the pH, 10 to the negative concentration, which in this case is 10 to the negative, sorry, I totally said that wrong. Negative log of hydrogen ion concentration, or negative log of 0.25 gives your answer of 0.60. And remember, it's asking for pH. So what's not been done here is you see it just says pH equals this. On the actual answers, just make sure it's clear what you're doing. pH equals pH equals 0.60. Just remember, 0 goes before a decimal point. Correct number is sig figs. pHs don't have units, so what you do is you just have something in there to make it clear that you mean a pH. Because if all we see is 0.60, we don't know what that means. It could be pH, POH, hydrogen ion, hydroxide ion concentrations. So just be clear what you're talking about by making sure there's something in the box answer that tells us what it is you intended to say. So, all right, let's see. There's more to practice with. And when it is concentration of strong bases we're dealing with, or just calculations in general with strong bases, it's going to be the same idea. Remember, what makes an acid strong is that it dissociates completely, and the same is true for bases. They are strong because they dissociate completely. We assume that means that every single hydroxide in that base, remember, hydroxide makes strong base, every single hydroxide is assumed to be released. So that means we assume that the concentration of bases equals concentration of hydroxide, at least in certain circumstances, which I'll get at in a bit. Here's a relatively simple example. What if we're asking for the pH of 0.10 molar sodium hydroxide? So we're giving you a hydroxide, which you should recognize that is not only a base, but a strong base, because all hydroxides are assumed to be strong bases at this level of the course. What you have to do is avoid a common mistake. In the past, people take negative log of this and think they have the answer because they forget that negative log of a concentration is going to be, well, actually, no, I take it back. You will do negative log of this, but here, let me get at what this is about. Make sure that you're paying close attention to what you're being asked for. You do negative log of this, so I made a mistake by saying you don't do negative log. You do. But we have to keep in mind what it's getting you. When you do negative log of this, because you assume that this is the concentration of hydroxide. You see, look at the balanced equation when it dissociates. For every one sodium hydroxide, you get one hydroxide. So concentration is going to be the same because it's a 1-to-1 balanced equation. So what that means is, okay, hydroxide concentration is this. So here's what people do. They do negative log of this. And this is what you get from negative log, but it's not the right answer because keep in mind, negative log of hydroxide ion concentration does not give you pH. It gives you POH. That's what causes problems with that's what causes a lot of issues. So do yourself a favor. POH equals this. So you can even do remember that you do not have pH when you do negative log of a hydroxide ion concentration. So what you have to do is convert from POH to pH using this equation. So you got to remember, rearrange the equation. Don't try and do it at the top of your head. But so pH plus POH equals 14. Subtract pH from both, or subtract POH from both sides. So we're trying to find out what pH is. So 14 minus POH is going to give you the pH. So 14 minus 1.0 gives 13.0. All right, this is your final boxed answer. Now, something to point out, people might ask, how come 2 sig figs, 2 sig figs, 2 sig figs, 3 sig figs? Yes, this is 3 significant figures. Why do you go from 2 significant figures to 3? And the answer is because you're subtracting. You don't count sig figs, you count decimal places. Notice, tenths place, tenths place. Okay, so make sure that you're paying attention to how you route for these significant figures. All right, again, subtraction means watch your decimal places. So having mentioned that, I think that should take care of that part. Look at this one. It's 2. That makes a difference. Okay, if you have 0.1 molar this, you do not have 0.10 molar of this. There's 2. I know with H2SO4, earlier we said ignore the fact there's 2 hydrogens because it only releases one of them. But that is only the case for sulfuric acid That is not the case for any of the bases. If you see two hydroxides here, they both get released. If you had aluminum hydroxide, oops, need parentheses, with 3, you would assume all 3 get released. Okay, that is, again, definition of a base is it releases all of its hydroxides, or a strong base releases all of its hydroxides. So here's what we have to do. Look at this balanced reaction. For every one of these, since there's 2 hydroxides, you get 2 hydroxides. So the hydroxide concentration is twice as much. So if you have 0.1 molar this, you have 0.20 molar this. So because of that, here's what you can do. You still are going to take the negative log of this to get this, remembering that that gives you not pH, but POH when you take negative log of a hydroxide ion concentration. And then you have to convert from POH to pH in order to get what this is asking for. Which means it winds up being 14 minus POH gives pH, so 14 minus that gives the answer. Again, this goes to the hundredths place, so your final answer needs to go to the hundredths place, because when you subtract, you count decimal places, not significant figures. This is what you want a box. And this infinite sig figs is just pointing out that don't worry about this 14 when it comes to rounding. It doesn't affect your rounding. All right, so I think, yeah, there's some more to practice with, and then later on we'll talk about acid-base titrations.